Right, so let's get into studying the normal distribution. The normal distribution is identified by three main characteristics. The first is the symmetrical shape of the normal curve, which is otherwise known as the bell-shaped curve. It is unbiased and has no skew, but it doesn't mean that all probabilities are likely to happen. All outcomes still have different probabilities, but the difference is that as you stray away from the mean, as the standard deviation increases away from the mean, from the first standard deviation to the second standard deviation, it becomes less and less likely to happen. The second characteristic is the unimodal peak, in which it is only one peak, and this creates equal median, mean, and mode. In the 18th century, French mathematician and consultant to gamblers, Abraham de Moivre, wanted to conduct an experiment and answer this one simple question. What happens if I flip this fair coin 100 times, and what will be the probability of me getting head 60 or more times? But since the normal distribution wasn't invented yet in the 18th century, Abraham had to rely on the normal distribution. The binomial distribution, in which he had to add up the probability of every single scenario, which means if he wanted to find the probability of getting 60 or more heads, he had to account for the probability of getting 60 heads, the probability of getting 61 heads, the probability of getting 62 heads, all until the probability of getting 100 heads. And then in the end, he had to add all of them up after he counted all of them using the binomial distribution. But he said to himself, this is too long and it's too tedious. Why do I have to count manually for hundreds, thousands, or even millions of scenario outcomes using the binomial distribution? It's ineffective and it's a waste of time to do so. But from this experiment, he found one useful observation, which is as the number of scenarios increase, the graph slowly becomes more and more symmetrical. Hence the name normal distribution or the bell-shaped curve. Here, in the first graph, in which we use the binomial distribution to count, it is done 2 times. The coin is flipped 2 times. And in the first trial, he got 0. In the second trial, he got 2 heads. And then he counted the mean, right? The mean is 1. It's quite symmetrical, right? As you stray away from the mean, which is 1, it decreases in probability. As you stray away from this side to the right side, it also decreases in probability, and it's equal. See, you can see that the probability of getting 0 heads and 2 heads is both 0.25. But the same logic applies if we increase the number of trials, let's say to 12. Those 12 outcomes, the median is 6, and it's the most likely to happen. But as we stray away from the mean, let's say we want to get 3 heads, it's less likely to happen because again, it's symmetrical, and this is the observation they found with the probability of 0.5, which is the number of getting head. It's less likely to happen if you stray away from the mean. Due to this, Abraham was able to form a new formula, which is the normal distribution. And it's basically the binomial distribution, but different. It's used to account for more than 60 scenarios, more than 60 trials. So it's kind of like an approximation instead of distribution. Normal distribution is found and used everywhere. It is used to calculate continuous and infinite outcomes for every solution, in which there are no set values. Let's talk about heights and weights. Let's say I have a height of 75 inches, and my friend has a height of 75.0001 inches. Maybe that difference isn't that big, but if you enlarge it in the normal distribution, if the normal distribution graph is enlarged, it's different. It's not the same height. It's also used to calculate for academic performance and quality control in manufacturing. How many products are suitable enough to pass the barrier of acceptance, and how many aren't. This is the normal distribution formula. X is the score, mu is the mean, and this is the standard deviation. Standard deviation is how many times you're away from the mean. The mean is the average of all the probabilities, and X is the score we're trying to count. Here, this is how you calculate the mu and the standard deviation. Number of trials times probability of successes for the mean. And for standard deviation, the square root of number of trials times probability of successes times probability of failures. To use this formula, we input the z-value, and we later find the area of this. This is the area, and each z-value gives a different area, in which I will show later. But the rule of thumb here is that the z-value will always cover the area from its left side to the maximum border. So this z-value will cover this area, and that's our probability of all these different outcomes. There's also a formula that accounts for the probability of z to the right, but it's very rare, and it's not standard. This is the normal probabilities table, in which each z-value represents an area on the graph. So let's say the z-value is 0. That means it covers half of the area. So that means the z-value stands here. To find the area on the right, it's really simple actually. You just have to 1 minus total area of the z-value to the left. Simple. Let's answer question 1. Question 1. The Edwards Theater chain has studied its movie customers to determine how much money they spend on concessions. The study revealed that the spending distribution is approximately distributed with a mean of $4.11 and a standard deviation of $1.73. What percentage of customers will spend less than $3 on concessions? So from the question here, it's stated that it is not approximated normally, and we already have the mean, standard deviation, and also the score. So it's really simple. We just need to input them inside our normal distribution formula. So in this case, we'll write down all of our given data, which is mean $4.11, mean $4.11, and then we have the standard deviation, which is $1.37, right? We also have the spending threshold, which is the X score, the one we want to test for, and it's $3. Okay, so we just need to input them inside this formula. X minus mean divided by standard deviation. And this is to calculate the z value. And remember, the z value isn't the this is the z value. Remember, the z value isn't definite, and it means that it only represents, it's a number that represents an area on the graph, but we have to check the z table first in order to find what the z represents for. How much area does a z cover? So we input it, so it becomes 3 minus 4.11 divided by standard deviation, which is 1.37. And after doing this, we get an answer of minus 0.81. Now, we can go with two ways here. The first way is we can use this 0.81, the z value, and input it manually. So that means by making it in a positive form, like this, right? Positive form. But and then we check the value of this minus 0.8, no, positive 0.1 on the z table. But if you have a calculator, we can do it instantly. We can input the z value, the negative z value. It's equivalent to z less than minus 0.81. So it's equal to 1 minus z less than 0.1. So it's just the positive, 1 minus positive if it's the negative. So it's interchangeable. So we're going to use this one, the instant way to calculate the z value if it's negative. P of z less than negative minus 0.81, and we get an answer of 0.2090, otherwise known as 20.9%. That is the probability of the movie theaters spending, the customers of the movie theaters spending less than $3 on concessions. Moving on to question 2. The length of human pregnancies from conception to birth approximates a normal distribution with a mean of 266 days and a standard deviation of 16 days. What proportion of all pregnancies will last between 240 and 270 days? This gets a bit tricky because we know every information just like the question we did before, but we now have two x values. So how do we solve this? First, let's write down all our given data. The mean is 266 days. The standard deviation is 16. And we know that it's normally distributed. So 266, comma, the variance, which is the standard deviation squared, right? We have it already. And now for the interval of x is 240 less than equal to, this right here, right? 270. It's inclusive. So what do we do here? Well, we just have to use logic. So we know that this is the graph, right? Graph of the normal distribution, and 270 sits right about on the right side, while 240 sits towards the left side. And we know that in the z table, we estimate the probability of the z going to the left. So it covers. So let's assume that if the value of 270 sits right about here, that means it will cover this portion of the area. Let me use a blue marker. I'll cover this portion of the area. Right? Cover that area, that side of the area. But 240, if it's here, it will cover the area towards its left side. So where does it cover? It covers here. There's an overlap, right? So we want to find the area in the middle between 240 and 270, which is this range right here. So it's this. What do we have to do? So it's simple really. It's just need to find both of the areas. First, the area covered by 270, and then we just subtract that with the area covered by 240. So the area covered by 270, we need to find the z value of it first. 270 minus the standard deviation, 266, divided by minus the mean, divided by standard deviation 16. We get the z value of 0.25. And then we just
use a calculator or a table, the z table, to find the area which it covers, and the area is 0.5987. For 240, we do the same thing. 240 minus mean divided by standard deviation, and we get the z value of negative 1.625. Again, there are two ways to solve this, just like the question we've done before. We can either 1 minus positive of the z value, of the modulus of this negative z value, or we can just instantly find the probability of z less than negative 1.625, and we can input it inside a calculator. And so we get the total probability of 0.0527. This is the 240 to 70. So what do we do here? So we need to subtract 270 from the 240. So we take these two probabilities and we subtract this 240 from this. So it's going to be 0.5987 minus 0.0527. And then it will give us 0.5460. This is the total probability of the proportion of all pregnancies that will last between 240 and 270 days, 0.460. Oops.
What if we need to convert other distributions to normal? Of course, there needs to be requirements. Right? There are certain requirements if we want to convert binomial to normal or Poisson to normal, and they all have one common requirement, which is to give or to add a continuity correction. I'll explain that later, but let's focus on each distribution for now. So for binomial to normal, we need to fulfill if the number of trials are more than 50, it's suitable. And one more, if the number of trials times by the probability of successes is more than 5, aka the mean, it's also suitable. These two are requirements. If one of them is not fulfilled, that means we don't use the normal distribution. And if they are fulfilled, don't forget to add the continuity correction. And then if we want to convert a Poisson to a normal distribution, if the lambda or the NP is more than 15, that means it's suitable. And we need to add a continuity correction after that as well. So what is a continuity correction? So basically, when we're calculating binomial distribution or Poisson distribution, we account for accountable and discrete outcomes, and they don't give us a range of infinitely possible values or continuous data like normal distribution does. So we have to approximate it. It's different from the set values that binomial distribution provides. So let's see here, if the probability of it is a in discrete form, we give it a range minus 0.5 and plus 0.5. If it's less than equal to a, we add 0.5. But if it's less than a only without equal to, we subtract 0.5. If it's more than a, we subtract 0.5. But if it's more than a without equal to, we add 0.5. So this is just like giving whether to give an extra or smaller range to include the values. If it's more than, we give it a larger value, like a larger area. But if it's not equal to, we just shrink it so we can all these without touching the border, without including the border or the number. That's the score. Here we can see the rectangle bars are actually the binomial distribution graph, and they're discrete. They have a fixed set of values. But when we use continuity correction, which we need to use in order to get a normal approximation on these data, we get a more symmetrical and smooth bell-shaped curve, which is what we need to calculate these these distributions. These are the examples of discrete outcomes. Rolling a dice gives us the countable and set values 1, 2, 3, 4, 5, 6, a fair dice. The number of cars passing a certain point on a road in an hour. It's not like 1, 1.5, 2.6. It doesn't work in decimal points. Number of cars are integers and will always have a set values. Will never be decimal, never have discrete, and never have continuous answers. The number of defective items in a batch, you can count them, and they are fixed. Example of continuous outcomes. Measuring the height of a person, as I've mentioned before, it's each centimeter or each inch matters, and it doesn't make a person the same height if their difference is only 0.01 inches. They're still different heights. The time it takes to complete a task, seconds, milliseconds, down to the last time it takes. It's uncountable, and it varies. It doesn't have a fixed set of values. The temperature in a room, it can be in decimal points, and it's not fixed again, so it's continuous. We have to use continued correction for these outcomes and for these trials.
We're going to start discussing question 3 now. A factory produces light bulbs, and the probability that a bulb is defective is P equals to 0.0.2, right? This is the probability of of failed and defective light bulbs. And the number of light bulbs the factory produces in a day is 500. So this is the number of total light bulbs produced. State the distribution of the number of defective bulbs, X, and verify if a normal distribution is appropriate. So we're asked to check and verify if it's this, which is in a binomial form, 500, 0.02, is appropriate to use the normal distribution. So we know that there are two fulfillments and two requirements if you want to convert the binomial to normal distribution. We have to make sure that n is over 50 and that np, or the mean, is more than 5. So we just need to make sure these two are fulfilled. And for question 3a, it's the number of trials is well over 50. It's 500. It's 10 times more than that. But for the mean, let's calculate it. 500 times the number of successes, and we get value of 10, which is again well over 5. It's 2 times more than 5. So from these two conclusions, we verify that the normal distribution is approximate and should be used in this question. So we verified that the normal distribution is accurate and suitable for this new question to calculate the number of light bulbs that are defective below 7, right? So what we want to do here is we want to list down all our given data just like we did in our previous questions. So mean is, as now we've calculated it, is 10, and for the standard deviation it's just square root of np cubed, right? np is the same as mean, so just 10 times the probability of failures, right? Probability of failures is the probability of failures 0.98, and then we get a value of 3.13 for the standard deviation. We have the essential two values, the mean and the standard deviation. Now just for the score. Is the score really 7? Don't forget that when we want to use normal distribution after we change our distribution to this distribution, let's say in our case we want to change the binomial distribution to the normal distribution, we have to add what's known as a continuity correction. So 7 it's less than 7, so it means it doesn't want to include 7 in it. So we have to make it smaller, right? Smaller than it usually is. So we subtract 0.5 from it. So our new score and our actual score that we will be using is 6.5. And then we just need to input all these given information inside our formula. 6.5 minus 10 divided by 3.13. Let's just input it in our calculator. 6.5 minus 10 divided by 0.13. 3.13. That's our z value. And we get negative 1.1182. Be as accurate as possible because you need it to be accurate when inputting it in the calculator or when finding it in the z table. So we can either do two ways from here. We can either 1 minus the probability of the modulus of this z value, or we can use it you can use the instant way using our calculator, which is p the probability of z less than negative of our actual negative of the z value we have. So that will be in our calculator. If we can just input it, we will get a probability of 0.13174. 0.13174. And this makes it around 13.17% of defective light bulbs below 7. This is our answer for 3B. Okay, let's move on to the next question. Question 4. When Profactory produces light bulbs, the number of defective light bulbs follow Poisson distribution with a mean of 25. Using a suitable normal distribution, find the probability that on a given day the number of defective light bulbs is more than 30. Again, more than 30. But here our problem is that using the Poisson distribution, we only have one data, and it's the lambda. It's 25. Yeah, it's 25. So where is our mean? Where is our variance? Why is there only one data? So if you've known already, the Poisson distribution is actually fulfilled and required to have similar mean and variance. So we can assume that this is our mean and variance. So we can assume that the normal distribution is just 25, 25, right? But again, we need our mean and our standard deviation. Mean is 25 as usual, and standard deviation is square root of variance, which is square root of 25, and we get 5. So we already have two important data here, right? As for our z value, it's more than 30. And 30 is not what we want because it's more than 30. It's not in our list, right? So we have to shrink down the border and include our nearest value, which is x more than equal to 29.5. This becomes our new z value, right? So we just need to input it in our calculator. So 29.5 minus 25 divided by 5 to get the z value. Sorry for my messy handwriting. Okay, so 29.5 minus 25 divided by 5. We get 0.9. 0.9. We just need to input it on our calculator. So we get 0.9, and then we input our calculator, and we get 0.81594. This becomes our probability. So the probability of getting light bulbs which are more than 30 in terms of effective light bulbs using this distribution Poisson is 81.59%. This is our answer for 3A. Now for 4B, we still use the same question, which is the number of defective light bulbs following a Poisson distribution of 25 with lambda 25, but this time it's inclusive of 20 and 30, so between 20 and 30. So just like the question in question 2, we just need to use logic. So between 20 and 30, if we draw the normal distribution graph, 30 will be here and 20 will be here, right? And this covers the area here, but we want the middle area between 20 and 30, so we just need to subtract 30. We need to subtract the 20 area, which covers this side, from the 30 area to get the middle area, the area we want, which is between 20 and 30. So we first take what we have, mean 25, standard deviation is 5. This is what we have, and we want to calculate each z value. So let's start with 30. The z value of 30 is x less than x less than 30. But here's the problem. X less than equal to 30. We need to add continuity correction too, again, just like we've said before. So continuity correction. And we want, since this is already equal to, we need to expand it, right? We need to expand it, so we give it an extra 0.5. We need to add 0.5. So x less than equal to 30.5. This becomes our new z value, the z value we're testing for. The x score, the new x score we're testing for. And so we put it on our formula here, 13.5 minus 25 mean and divided by 5 standard deviation to get the z value of 1.1. And if we input it in our calculator, the probability of z value less than 1.1, it will give us 0.686433. Keep this first. We keep this first. Now we calculate the area that the z value of 20. What is it? The z value of 20. 20 again. Okay. Again, don't forget to add continuity correction. This is x more than equal to 20, and so if more than, it means if we go lower, right here, this is 19.5. If we go lower, that means we include a larger area. So because it's more than equal to, we subtract 0.5. So it becomes 19.5 less than equal to x, right? And now this becomes our new z value, our new score actually. 19.5 minus the mean divided by our standard deviation 5 to get a z value of 19.5 5 minus 25 is negative 1.1. This is our new z value, negative 1.1, and we just need to input calculator, instant form less than equal to minus 1.1 directly, and we get a probability that covers, which is 0.1357. 0.1357. Oops, this is too messy. 0.1357. 357. So we already have the score and probability of 20 here and 30 here. So we just need to subtract 20 from 30. Sorry, not this. Actually, it's not this. It's this. And we get 0.86433 subtracted by 0.1357. And again, calculator. We get an area of it covers of 0.2863. This, or otherwise known as 72.86%, is the probability of defective light bulbs between 20 and 30.
That is all. I hope you understand the normal distribution. It is an approximation that needs to be continuity corrected to calculate continuous and infinite outcomes. We can also convert other distributions, such as binomial and Poisson, to the normal distribution, given if it fulfills those requirements or certain requirements. And I want to thank these sources, which have helped me deepen my understanding of the normal distribution. And maybe if you're looking to deepen your knowledge as well, you can study these sources on a later time. Thank you.